And so our next talk is going to be from Axel Voigt from the Technical University of Dresden, and he's going to talk to us about epithelia tissue as a collection of interacting deformable objects.
Thank you very much, and yeah, thanks to the organizers for bringing this here together. Well, already the title says that there's some contrast to what we heard before, so it's the biological content in like ordering and geometry packing. But let me start with the people involved here. So it's Dennis Wenzel. He was a former PhD student. He now has his own company and making money in finance. But anyhow, Leah Happel, she is the PhD student behind all this newer results I show. And Jan Lischka, he also contributed. And then there's some work also from Harris Jane and Luisa Angeluta from Oslo. What I'm interested in is to describe morphogenesis, to discover some physics which drives morphogenesis. So here's just an example for one of these processes. What we see there are cells, or to be more precise, the nuclei of cells in developing thing. Let's stop. And the question is, for example, what are the physics which lead to the formation of these bumps, which then at some point form the limbs or so, right? So that's the idea. And so we have objects which arrange somehow, but there are certainly differences to this classical packing problem. So our objects are deformable. They are also active. They interact not only by excluded volume or friction, that there are also attractive forces between cells. And in the video, you see that you only see the nuclei of the cells on the periphery, let's say. So only they matter. So inside there's something else. So we have these problems on surfaces, and these surfaces evolve. Right. There might also be some similarities. So what biologists like to do is to look at like neighbor relations between the cells and look at defects there, so that not only like positional defects, also like orientational defects. If you interpret some of these things as like a liquid crystal, I will come to that. There are phase transitions. There's something like a jamming transition, but we can also consider like fluid and solid phases in this tissue, and there are, of course, out of this there are emerging elastic and viscous properties, and then we are interested in that. And I have to stick, right? I will go through all these things and describe how we model that and what we can do with this. Oops. So let's start with objects are deformable. And maybe the one approximation we do is we described our objects as 2D, our cells as 2D. So there's no height of our cells. And we use an implicit description for our cell, and we use a phase field function phi, which is in such a way that we want it to be, let's say, -1 outside the cell and 1 inside the cell, and then we have some smooth transition for this cell boundary. And the way to do this is to define a free energy, such a Cahn-Hilliard-like energy with a gradient term. So this kind of analyzes changes between these two phases, inside and outside, and a double valve potential which has the minima inside and outside. And then we have this small parameter epsilon, which is a length scale for the smeared out interface. And then we define some gradient flow in such a way that it's a conserved evolution, so the area is conserved. So in this community, that might look like the most expensive thing you could do to describe a 2D object, but it comes with some advantages that these things are really or can deform, and we have a continuous description of it. So this has just some regularizing effect. So it evolves to a circle, area is conserved, and we have a material parameter, this capillary number, which models the softness or stiffness of this cell. Okay, so we have deformable objects. The next thing was that our objects are active. So active in this sense means that they have some chemical energy, and they transform this into motion or deformation. And the way this is modeled here is by considering an convective term in our Canhilliard equation, and this velocity we describe by like a self-propulsion velocity, some strength of the activity, and let's say some direction. And now there are various ways to describe this direction. So I just point out two. Well, the simplest probably is to say, well, we choose a random angle, and this follows some Wiener process, and then well, inside the cell, our velocity is our activity is constant, and it moves in one direction, and then it changes. So that's maybe a generalization of an active Brownian particle to deformable objects. Another idea, well, there's probably not too much biology in this, but another idea, some effective way, is to say, well, let's say the cell moves in the direction of its elongation. And we can get out the elongation of the cell by such a shape factor. We can compute from our phase field function phi, and well, the eigenvectors of this shape tensor then gives us the elongation or the contraction, and we can use this to specify in which direction the cell should move. So, well, an illustration here already in the context of that we have more than one cell. Yes.
So what the V is a function of space, and it's different for each cell somehow?
Right. So in the moment I only talk about one cell. So
okay.
Yeah.
But you have some way of determining where the cell is.
Yeah, the cell is implicitly determined by the phi. So where phi is equal to 1, there's a cell. Where phi is equal to -1, there isn't a cell.
But then how do you, every cell is like that?
Yeah, so far we only have one cell. Yeah.
Okay, got it.
Yeah. Right. But there are various other things. So taking into account subcellular details, such as liquid crystal within the cell and some splay instability or whatever, so the motion, or taking into account like neighboring cells or some alignment properties and so on. Well, we will stick with a kind of combination of this, so go in the direction of elongation, but with some noise. Okay, now, well, the question is, there's not only one cell, there are many cells, so we have to add more cells, and well, the way to go is, well, instead of considering only one equation, we now have n of these equations, n the number of cells. And then in addition to this Canhilliard energy, which is now modified, we just sum over all the cells, we have an interaction energy to take into account. So that's this one. And one way of, effective way of modeling repulsive and attractive interaction is this. So we have this double sum, and this models repulsion, so it kind of penalizes that two cells are on top of each other, and grad phi is the model is essentially just the interface, and if this is negative, then it kind of favors the overlap of the interface, and that models attraction. And the tilde here is just the shift, not that phi is between -1 and 1, but between 0 and 1. That's more appropriate for this form. Okay, so we can do this, and here's an example of a couple of cells in some periodic boundary, and some are color-coded, and they move, and they deform, and they undergo some T1 transitions, and so on. And now, well, what we have to solve is this coupled system of n equations, and it couples through that. Maybe some comment on how we do this. Well, each cell is solved on one processor, and then we need the communication between this, and the algorithm kind of scales with the number of cells, at least to like in the order of like 1,000 cells, even if I only show like results with like 100 cells in this order. Okay, so we have many cells, they interact, they deform, they are active, they do something. Oops. Question is this already useful for something? Yep.
You said they move, but I think I missed. Are you doing a conservative motion in time, or is it a gradient? What's the law for motion? That's what I'm missing.
Okay, so the law for motion. Let's go back. The law for motion is this. That's the law. So we specify some activity that's how it sets. So it's a okay. Okay. Question is, while we are still in 2D, question is this already useful for something? And well, first of all, we could well, even if I showed the video with cells which all have the same size, we could have different sizes. And then a question would be, well, can we reproduce known relations between neighbors from like passive systems like this Lewis and other wire law? And they indeed also for this active system nicely can be described by these laws. Okay. Other things, well, we can look at like cells in some petri dish. What do they do? And well, what people found is that they do some oscillations. So we also can kind of follow trajectories of our particles, of our cells, and they also do like such kind of oscillations. So that's fine. Something more physical, maybe. We can vary the two parameters we have in our model. So one was this capillary number, modeling the softness of our particle, and the other was this self-propulsion mechanism, the activity. So the packing fraction here is not varied, it's fixed. But if we do this, then we get a solid liquid phase transition, right? So that's also something which has been measured. Okay, so this is fine. Another thing we can do is, well, we already have kind of this the shape tensor, and what is shown here is this direction of the largest eigenvector, and out of this direction we can now, well, do some smoothing and define some nematic field overall. We get this and identify defects in this nematic field. So we get typical 1/2 defects, -1/2 and +1/2 defects. We can track them over time, measure velocity and so on, and to look at like distributions of this. And indeed, one finds some difference between -1/2 defects and +1/2 defects. We can also kind of look at in which direction they move. And well, here, for example, the difference between like the only random model for the activity and this elongation model. For the random, there is no difference. The elongation model, well, there the +1/2 defects move in the direction of the defect. Okay, so that's in like 2D, and there are other things. But well, we want to do this on a surface. And well, we start with a simple surface, a sphere. However, we can formulate our equations for general surfaces. And so far, we are only discussing like scalar quantities, so it's relatively simple to extend this to surfaces. So it's essentially just replacing all the operators by their surface counterparts, so we're using the covariance derivative there. And then we can well, initialize this and run this on the surface, and we essentially get similar results there. Okay, now for like small number of cells, we indeed get some equilibrium configurations, and here, well, low activity actually helps to find this, well, they are certainly related to like equilibrium configurations for the Thomson problem there. However, if you now look at these, our phase diagram for the capillary number and our activity there, so that was the one from 2D. What we now found is that kind of in between this solid and liquid, we have another state, and that's a collectively rotating state. So kind of if we increase the activity, then instead of breaking all the bonds and so on, this thing can move collectively, keeping the configuration, and it just rotates, right? And this, well, it somehow gets lost if there are more and more cells, but at least for small numbers of cells, one finds this also in embryos where one has this collective rotation. Okay, so that's some new thing where like curvature and topology comes into play. And besides that, well, we can do the same thing. So identify the elongation and get a pneumatic field, some surface pneumatic field, and identify the defects and look at like number of defects over time. So at least on average, we have like 2 -1 and 6 +1 half defects, so they add up to 2. Well, fine. But there's some difference in the lifetime, and at least for larger driving forces for larger activity, there seems to be also some difference in like the defect speed between the different types. Okay. Now what else? Next, more general or more complicated surface, whatever, would be some cylinder. And luckily, there are experiments for cells on cylinders which have been done. And they have looked at like NDCK cells on the cylinder, and we're interested in what's happening. And here's some video. We again see the nuclei of these cells, and well, to some extent, they are potentially more rotating than moving along the cylinder. And one can quantify this within these chymographs or looking at the average velocity. So there seems to be some effect. Now, what is the difference now? We have now, well, Gaussian curvature 0, and we have 2 different principal curvatures. And indeed, there are various experiments also done for single cells, and they seem to align with minimal curvature directions. Maybe not all cells in the same way, but there seems to be some effect. And this is attributed to like alignment of the regulating network filaments within the cell with minimal curvature direction. So similar to like liquid crystal things on curved surface. The other explanation is that, well, of course, the cells are 3D and there's a nucleus and so on, and they align in such a way that there's the least nuclear mechanical stress. However, within our 2D picture, this is, of course, more friendly, and we go with that. So let's try to see if our model also captures this. And, well, I mean, if we only solve this Kahn-Hilliard type equation on a curved surface, then we don't see this effect, right? It converges to something, and for such a ruled surface similar to the cylinder, what we get is just a geodesic circle. So there's no alignment of this just from this count. However, well, if you have like tangential surface vectors or tensor fields, then they typically respond to extrinsic curvature, and in the way that like they align with minimal curvature directions. And the idea is now to use the elongation of the cell defined through this shape operator. So I was calling this S before, but what it actually is, it's a Q tensor. Let's call it Q. So we get this anyhow. The only difference now is that the derivative here is always with respect to the tangent plane. And now we can borrow this connection from like nematic liquid crystals. So this relates to this director field. And now in this surface liquid crystal models, one can derive this rigorously from like 3D models. Typical term there is like this gradient of this director field. So we had this yesterday in 3D. And what is essential for the surface models is that it's not only the covariance derivative which matters here, but some additional term which models this extrinsic curvature. So nu is the normal to the surface, B is this more extended Weingarten map. And this is the term which leads to the alignment of the director field with the minimal curvature lines. And the idea now is to simply use this and add it to our model. Okay, now we translate this in our phase field description and add this additional energy to our energy, our Cran-Hilliard and interaction energy. And then solve the model. And here's an example on a cylinder where like the trajectory of 3 cells are highlighted. And that leads to some rotation. And if we look at the chymographs, you already see that. And I mean, the effect is not too big, but there is some preferential rotation. And we can now quantify this. So the difference here is so we have different cylinders. The curvature increases in that direction, and we change the sign of this factor so that we have a preferential orientation in that direction or in the other, or at this 0. And then it's kind of the distribution here of the velocity field of all our cells. And at least for strong curvature, we see this preferential motion in these different directions. So we can reproduce these experiments on the cylinder. Now the cylinder is also not too complicated. So the next thing would be maybe some torus. So now we have varying curvature. We can do the same game. Well, again, different tori and different preferred orientation, but we find out that well, the velocity is not really affected by this anymore. So it seems like that the intrinsic curvature here plays a much more severe role. However, the elongation, and this is shown here, has some preferred orientation. And what we now can do is well, look at this as a function of the Gaussian curvature. So we kind of bin different parts of our torus and look at how is the velocity and the orientation kind of what is the angle between this with our tangential direction. And that seems to depend on curvature. Well, there are some experiments, but they're very rough, showing the similar trend. But what take-home message here is that, well, for this more general surfaces, this extrinsic curvature might not be that important. Okay, and well, you could now say, well, there's still surface is still not moving, right? So that's what I wanted to show. But we make some progress. Well, that's kind of some very recent stuff just to demonstrate that, well, numerically, we can handle this as well. Here we prescribe the evolution going from a sphere to an ellipsoid. Whole thing follows this, that works. Of course, the goal at the end is to come up with some physical law for this evolution, depending on the arrangement of the cells on the surface. Okay, with this, I'm at the end. Thank you.
You mentioned a solid liquid transition and function of capillary number. So the capillary, as I know it, is the ratio of viscosity and surface tension. Could you say how this relates to the parameters of the Cahn-Hilbert equation?
Yeah, okay. So it's well, it's a surface tension. It's just a non-dimensional number. I don't have viscosity in here.
But what do you call a capillary number then?
Yeah, it's okay. It's a non-dimensionalized number, which well, where the only physical thing besides length scales enters is the surface tension.
That's why in the Cahn-Hilbert equation, the gradient term, grad phi I, is not squared.
Oh yeah, that's missing. Thank you. Yeah, that's wrong. Yeah, that should be squared, of course. Yeah. Sorry.
Very, very nice. And more in the theme of what else could you do, right? I'm sure you thought about this, but I wonder if you could comment. You can imagine studying growth and depth. Is that in these models? Is that a
Yeah, well, you can do growth and well, that's, yeah, we haven't done
that's
that.
the reason?
Yeah.
In
Well,
this context, it's
sure.
a differential growth that's coupled very strongly against
Yeah.
curvature.
right. So we have generalized this multi-phase field models to incorporate growth and also cell division. So there's a paper from last year, but only in 2D. We haven't done this like on the surface.
And what's you just have a source for mass, time-dependent source for things to grow.
Yeah, we say there's infinite amount of whatever available, and it's just growing by some linear growth law. And if it reaches some size, then it divides. But of course, it can't grow because there's contact inhibition with the neighbors and so on.
So you showed in the last slide also an ellipsoidal, and in embryogenesis, there's often they form these kind of ellipsoidal clusters there, where you also get vortex formation on the umbilical points, basically. Have you also tested this, and could you also generate these kind of dynamics during embryogenesis?
Well, we are not that far, so it's yeah, so it's yeah, it's just well, we proceed step by step, and now we kind of solved the issues, the numerical issues to do this on some evolving surface with all this parallelization and so on, and well, to look at something like this well, certainly is the next questions.
Yeah.
Oh, I don't think I have a question.
Okay. Okay, great. So we are going to come back at 1:45 for after lunch. Okay, and we have lunch now. Let's thank our speaker.